A confirmation about the audio, please, if the audio is clear and available. Thank you. Kishan, if I'm not mistaken, you had actually sent uh, a copy for evaluation, right? So that is the only portion which is left, and rest of your mails have been replied to, as far as my memory tells me. See, for paper evaluation, it takes some. If generally I don't take up paper evaluation, so sometimes when I do, it does take time. So I don't want to rush into it, but I will give you and I'll furnish the feedback to you by tomorrow. Okay. Is there any other issue that you have? Okay. So I guess that was the issue. Okay. See, the last thing that you can do to damage yourself and your preparation as of now for all the candidates is to start panicking. The moment you start panicking, that there is very little time which is left, that is the moment when you start committing mistakes in terms of your process that you follow for your preparation. So still there is time. There's not a lot of time for next year, but there is time that if you're honest enough on a daily basis, on a day-to-day basis, still there is a lot of time for you to clear the examination. But for that, obviously, day-to-day sincerity is involved. So don't panic. You will, if you are on the track, if you are following the process, it will happen. Don't worry. Okay. Just a couple of minutes, guys. Okay. So let us carry on the discussion where we left off yesterday. So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Now, yesterday we had looked at the basics when it comes to atmospheric conditions and what do we understand by the atmosphere, the different layers associated with it, the role played by each of these layers, the process of heating and cooling as it is observed, and also the impact that we have when we observe the temperature change, the factors which end up influencing the variation in insolation, the factors which end up influencing the variation in terms of temperature. What do we understand by urban heat island? What do we understand by temperature inversion? All those factors we have delved into significantly greater detail. Now, any doubts that you have in that aspect, please let me know while you were covering, or in case you have revised the portions. Satish, is Earth albedo is 0.3 or 0.2? See, on an average, it is taken to be 0.3, but then the actual variation of it does happen. It does lie between 0.2 to 0.3 on an average. So when we talk about the exact amount of solar rays which is lost to the outer space, it comes out to be 0.23 to 27. And it is not always consistent. So hence, on an average, you can consider it 0.3 or 0.2, any of them. And then Himanshu, what is Karman line? So Himanshu, Karman line basically is a kind of a think about it, a imaginary boundary between the atmosphere and the outer space, and it is not exactly going to be the end of the atmosphere. That is why Kármán line is basically representing the homogeneous part of the atmosphere up till the mesospheric region. That is where the Kármán line to the top of it exists. Beyond that, you have thermosphere and exosphere, where you don't come across such a uniform behavior in the atmosphere. You come across various different haphazard movements. And Himanshu, subsidence inversion is basically when we talk about the airs, which is, or a large mass of air which is sinking from the upper atmosphere in the middle to higher latitude. Now, that large mass of air undergoes compression, due to which there is an adiabatic heating. If that adiabatic heating leads to the temperature even slightly higher than the ground temperature, that can cause an inversion condition, and this inversion is caused because of subsidence of air, hence the name subsidence inversion. And because it is happening in upper region of troposphere, hence it is referred to as upper air subsidence inversion as well. Okay. Albedo of the ocean surface is less. Satellites generally are above, much above the Kármán line. Pranay, ozone in stratosphere is good ozone, in ground surface is bad ozone. Yes. Utsav, adiabatic heating is basically when there is a heat gained by a parcel of air by pure change in volume. Generally, we see how is it that the air gets warmed up. When it is in contact with the ground surface, when it gets heated up, then it is that air warms up. Or when it is in contact with the cold surface, that is when it cools down. But the air can basically, the air particles can also exhibit a change in temperature by virtue of the change in volume also. So if, let's suppose, there is a compression of the air parcel or any air column, now what it will lead to is the particles will be confined in a lesser space, so they will go for more collisions and vibrations amongst them, and that will lead to a spike in the energy, and that is what leads to the heating, which is referred to as adiabatic heating. Okay. Now, after this, we come to the portion of atmospheric circulation. And here, this is the portion which is relevant both for your prelims as well as your mains examination. So for your prelims, here, if we talk about this, what is it that it is relevant in your prelims examination and for your prelims preparation? You will find areas such as permanent winds, pressure belts. Where are these? Okay. Then local winds, that is the region where they are in existence. Prevailing wind refers to the wind which is in existence. So advection also leads to the various different types of temperature distribution that also influences temperature. So that is where the role of prevailing winds comes into place. Regions of existence, where is it that which kind of local wind would be in existence? By the way, guys, from the portions that we have covered yesterday, it is the later portions which are going to be much more relevant, both from the conceptual perspective as well as direct questions are always asked from that area in the prelims as well as in the mains examination. So even while revising those particular module or the previous module, please do ensure that adequate focus is paid upon the area of temperature inversion, adequate attention is paid on the area of isothermal variation. Why is it that the isotherms bend in a certain manner? In which manner do they bend as they move from land to water during the winter season? And why is it so? And during the summer season, and why that is so? So UPSC has asked multiple questions from that area and has repeated that area multiple times. So this is just a kind of a Q-tip for all of you guys, that please ensure that that particular portion, once you have covered in significantly greater detail with a very slow pace, that is revised and that advantage is not lost by you guys. Okay. Now, here in the mains examination also, you basically can expect a question about the permanent winds and pressure belts. So that is the area which is frequented by UPSC in its examination and the question that it frames. So in this particular module, we are going to cover the areas when we talk about, let's suppose, the existence of pressure. What do we mean by pressure? What leads to high pressure and low pressure? Is it purely driven by the existence of only temperature, or is pressure influenced by the movement of winds as well? Why is it that the movement of winds happen at all? What are the factors which will influence the wind movement? What do you understand by the pressure gradient force? What do we understand by the Coriolis force? What do we understand by the frictional force? And then, based upon all those, we will basically be analyzing in detail about the permanent wind systems which are in existence across the entirety of the planet. And in which region do they blow from? And how is it that these wind systems are basically named? That is something that we are going to study. And then eventually we are going to understand the concept of local winds. What are local winds? When we talk about Lu, when we talk about Chinook, Phone, Sirocco, all these, Mistral, all these are various different categories of local winds. So why do they come into existence? Where do they come into existence? That is much more pertinent and relevant for your exams. And that is what we shall be concentrating upon. So without further ado, let us initiate our discussion. So basically, we initiate the discussion from the portion of pressure. That is, atmospheric pressure is what we will be studying here. So what do we understand by atmospheric pressure? In simplest of the terms, pressure exerted by the atmosphere. What is pressure? You would have heard about pressure multiple times. What do we mean by pressure? So pressure is basically the force exerted per unit area on any particular surface. That is what is pressure. So when we talk about atmospheric pressure, what is it exactly that we refer to? So for any particular surface here, let's suppose we consider any particular surface. Now for that particular surface, if you consider the top of the atmosphere as well, let's suppose. So at any particular region on the surface, there will be force exerted by the mass of air. The air particles which are present, these air particles will exert significant amount of pressure or their weight on the ground surface, isn't it? Because they are attracted by gravitational pull, and the gravitational pull of planet Earth is significantly strong. So all of them, they will be exerting their weight on the ground surface, and that is what we accrue as the factor of, or the fundamental of, pressure. Okay, so this is what we refer to as the atmospheric pressure. Now, atmospheric pressure is not consistent all over the planet Earth. It varies. It varies upon the region. It varies upon, if we consider a particular height, if we consider any particular area which gets heated or is cooled down, there also atmospheric pressure is varied. Now, here, yesterday we had looked at certain basic concepts, and the concepts that we looked at was basically when the air gets warmed up, when the air gets heated up, it tends to rise always, isn't it? And subsequently, when the air is cooled down, when it becomes colder, it becomes heavier and tends to sink. That is something that we have already seen. So let us write that inference here itself so that we are able to formulate various different conclusions based upon that inference. So warm air tends to rise up. Until when will it rise up? Is it so that once you warm up an air, it will continue to rise as long as it reaches the outer space? No. It will rise up as long as that air parcel is warmer than the surrounding. That is the extent, or that is the limit to which it will continue to rise up, isn't it? So warm air will rise up till the point that it reaches the top, or basically the area where it is still warmer than the surrounding. As long as, or as soon as the temperature becomes consistent, then it won't rise any further. Okay. And as long as it is warmer than the surrounding. Okay. Now, when we talk about cold air, so cold air is heavier, right? Why? Think about the logic here. So, the same logic which drives that why is it that the warm air is lighter, the same logic will give us the response of why cold air is heavier also. So, why do we say that warm air is lighter? So, if I consider any pocket of air, now it will have various different molecules, it will have various different particles included within it. Under normal circumstances, when we talk about the weight of the air parcel, that weight will basically consist of the weight of all these particles, including water vapor, etc., everything, right? Now, if I heat it up, then all these particles will gain some or the other form of energy, right? They will have some of or the other form of kinetic energy. Kinetic energy is that energy which is accrued, which brings about a kind of a motion or a movement. So heat energy that we provide to the air, or whenever air gets heated up by contact with the ground surface, the particles will also gain certain amount of energy. There will be a kind of a randomized motion amongst these particles, and many of these particles eventually will manage to escape the system, right? Because of the new energy that they have, many of them will be escaping through the system, and we find them outside this particular air pocket. So obviously this air pocket, after getting heated up, now as compared to earlier, will have less number of particles, and hence it becomes lighter. So that is why when it is lighter, it will rise up. But what is the case, or what is the situation when we say that the air has become colder? Why will it become heavier? So here also understand, when we say air has become colder, or the air has cooled down by contact or by getting in contact with the ground surface, you have to understand that cold or cold condition is what? Can we think about cold condition as extraction or removal of heat energy? When you remove heat from any particular substance, it will get cooled down. Simple, right? I will repeat it. When you remove heat from any object, any body, it will become cold. Now, heat is a form of energy. Energy had provided the particles with a kind of a motion that they could escape. But if I were to extract that heat energy, I am extracting the energy which is present in the various particles. So when I'm extracting the energy of the particles, they will slump together, they will get attracted with each other. That is the only energy which is left. They will try to coalesce together, they will try to come together. Now, what do you find? That in the same air parcel, now you have much more number of particles as compared to earlier, because you have extracted energy out of it, isn't it? And that makes this particular air pocket heavier. And hence, cold air is always going to be heavier as compared to the normal air parcel that we consider. So, with respect to that, when the cold air we say is heavier, it will always have a tendency to sink down. Okay? So, cold air is heavier and tends to sink always. Okay? Now, here, you have to think about it that this can influence the pressure of a region as well. So here, if I give you a condition, let's suppose, if, or let's consider a separate one altogether. Let's suppose here, the land gets very hot. Okay. The land has been heated during the summer, so the temperature has risen up. So obviously, the air temperature will also rise up. The air in contact with the ground, that will also get heated up. So its temperature will also rise up. So here, when you have the warm air parcel in this region, now that warm air parcel, basically, after it is getting heated up, it will become lighter. It becomes lighter, it rises up. So this warm air will rise up. Now, when the warm air is rising up, now what will be the impact of pressure? If suppose this is the ground surface and from here the warm air is rising up. Pressure is what? Force which is exerted on the ground. But if you have the air which is rising up, what will be the impact on pressure? Pressure will reduce, or will it increase, or will it remain the same? What do you think? Very good. Pressure will reduce, right? So as the air rises up, the pressure in this region will tend to reduce, always. So rising air parcel or a rising air column is always associated with creation of a low pressure for whichsoever reason, whatever might be the reason. But if the implication or the final effect is that air will rise up or air is forced to rise up, then on the ground surface, it will always induce a kind of a low pressure. Okay, because the pressure is what? The force exerted. And if that is removed, if the air is rising up, the pressure will reduce. So here, that brings us to one of the first major inferences and conclusions. That is, rising air causes low pressure. Always. Okay. Whereas, let's suppose in a particular area, the ground is cold. So the air in contact with it will also become cold, right? Isn't it? Now, if the air, let's suppose here, it becomes colder above it also. Now, as this air will start sinking, then upper air will also induce that sinking motion. So, because if this air sinks from here, there will be a vacancy created in this region. So, the air from this area will be drawn to fill that vacancy. And that is where you will have a sinking column. Now, that sinking column will hit the ground surface, right? And here, if suppose this is the ground surface, you have more air which is sinking. So, what will be the impact on pressure? It will increase the pressure which is felt on the ground. So always sinking air column is associated with creation of a high pressure, always. Okay. Now, again, I would repeat that the sinking air can be created by many factors. Temperature is one of the factors, but it can be induced by many different factors. But nonetheless, the outcome, the result of it is the same, that it will induce a high pressure. So sinking air column, sinking air causes high pressure. So a rising air causes low pressure. A sinking air causes high pressure. As simple as this. Now, rising air and sinking air, this phenomena can be influenced by temperature. Temperature is one of the factors which can influence this, but it is not the only factor. Okay, so the rising and sinking air can be created by multiple factors. It can be the condition that despite a high temperature in one area, you have sinking air. It can be the situation that despite the low temperature in an area, you have rising air, right? Or to put it more simply, it can happen that even when the ground surface is hot, still you can come across a scenario of sinking air. We will take a look at that when it happens, why it happens. And it can also happen that the ground is cold, still you have rising air. So temperature is just one of the factors which can influence this motion of air. But there are multiple other factors such as movement of air, convergence, divergence of wind, etc., that also induces this rising or sinking air phenomena. So this can be temperature is one of the factors influencing this. Just one of the factors. Okay. For cold air, it's more dense, then by adiabatic heating, the temperature will increase. Yes, it will increase, but not so substantially. If the temperature increases so substantially that it becomes warmer than the surrounding, then it won't sink any further. Then there the air will lie stagnant, or if it gets very heated up, it can rise up from mid portion itself. Right. So it is not always going to be the case that if it has started sinking, unless and until it will reach its destiny, that is the ground surface, the air will not rest. Not like that. If there is adiabatic heating, if there is compression, then if let's suppose that air parcel is acting independently, not driven by other forces, its movement can stall there itself. Okay, so that can always be the factor. Now here, when we take a look at it, what do we mean by it? So the weight of the column of air contained in a unit area from the mean sea level to the top of the atmosphere is called atmospheric pressure. It is expressed in the units of millibar, and the average atmospheric pressure is considered to be 1013.2 millibar. So if at any particular area the pressure which is experienced is 990 millibar, it will be a low pressure. If in any area you have the pressure which is experienced is 1020 millibar, it will be the condition of a high pressure. So it always tends to vary, the creation of high pressure and low pressure. So here, this factor of the variation in pressure or the rise and the fall of air, that in itself can induce a kind of a circulation of air. So, just to introduce ourselves to the very basics of the circulation here. Now, before we move into the details of it, we start with the very basics. So, suppose this is the surface, this is the top of troposphere. Now, under normal circumstances, as the warm air, let's suppose this ground is getting heated up, it is very hot. So, the air above it will also get heated up quite significantly. Now, this hotter air will rise. Will rise up till where? Will it be able to rise in the stratosphere? Will it be able to rise up till the level of mesosphere? Or will it be restricted only into troposphere? Why do you think? What do you think is the case? And why so? Will it be able to rise easily into the region of stratosphere? Good. Majority of you have given the correct answer. Yes, Akshay, very good. Subhash, correct. Ankit, correct. So most of you are correct in the basic logic that it will continue to rise up as long as it is warmer than the surrounding, or as long as the temperature is the moment that the temperature of the air becomes equal to the surrounding, that is where the rise will stop. So let us analyze this. Let's suppose the air has started rising up. Now, as the air rises up, this is the level of tropopause, let's suppose. Okay. Now, as this air parcel is rising up, here, after a point of time, as it rises up, its temperature will also cool down. It will become cooler and cooler. Why? Because the air, when it rises up, it has the tendency to expand. Okay. What we saw under adiabatic expansion, the air has got a tendency to expand. And as soon as the air expands, it basically loses temperature. That means it cools down. So as the air rises up, it starts cooling down. But then the argument is that it will rarely rise above tropopause. In very rare circumstances, when suddenly you have a plume of hot air rising, only in those areas will the air be able to reach the stratosphere. Otherwise, it generally will not be able to reach the stratosphere. And the reason for that is very simple. Because when you talk about stratosphere, there you have warmer air. As compared to the top of troposphere, stratosphere has got warmer air already. So this air parcel which has been rising up from the region of the troposphere, chances are that it will be so cold by the time that it reaches the tropopause that it won't be able to rise any further because the stratosphere is warmer. Okay, so stratosphere here the air is warmer. Warmer in comparison to what? In comparison to the ground surface? No, in comparison to the top of troposphere. Okay, so air is warmer in comparison to the top of troposphere. So that is why majority, in fact 99.9999% of the times, the air when it rises up, it will be able to rise only till the region of tropopause, not beyond that. Because beyond that, for the air to rise, it still has got to be warmer than the stratosphere. And stratosphere already starts indicating a rise in temperature which is experienced. So here what will happen? So as the air reaches the level of tropopause, it cannot go any further. It cannot rise any further. And meanwhile, let's suppose this air parcel has risen up from here, and this air parcel has reached here. So there is a kind of a vacancy here where more air then will get heated up and more air will start rising up, right? So more air parcels will rise up in the entirety of the process. Okay, so it is continuously pushing it up, but at the top of it, it cannot rise any further. So where will the air go? Air basically will have to diverge. Air basically will diverge like this. Okay, at the region of the top of troposphere. The top of troposphere already has a temperature close to around -60, -70 degrees Celsius, depending upon the season and the region that we are talking about. So here when it is very, very cold, so the air also starts slowly and steadily becoming colder and colder and substantially colder. After a point of time or after spending some time at this region, we can assume that the air will become substantially colder. And when it becomes colder, then what will happen? It will start to sink down. But why has it begun to sink down here only? Why not here? Why not here? So the answer is it can sink down anywhere, depending upon where it has lost its temperature, where it has become colder than the surrounding. As soon as it becomes colder than the surrounding, the air will become heavier, it will start sinking down. Right? Now, this cold air here, you have the cold air. You have this cold air. And that cold air continues to sink. Right? You have sinking air. Now, this sinking air will hit the ground surface. And when it will hit the ground surface, again, where does it go? So, this sees a kind of a vacancy created in the hot region because the air which was present has risen up. So, there is a kind of a vacancy created. So, this air will try to rush in and fill that vacancy. There will be, after hitting the ground surface, it will move in both directions actually, but some portion of it will go there to fill that vacancy. Right? Now, it fills that vacancy, and here again it comes in contact with the hot ground surface. Again, it will get heated up. Again, it will start rising up. It rises up as long as it is warmer. It will hit the region of the tropopause. Then it will diverge. After spending some time in the tropopause, in the region immediately below the tropopause, it will cool down. Again, it will start sinking. Again, upon hitting the ground surface, it will go to fill wherever the vacancies are there. And that is how you have the circulation. So on the ground surface here in this region, what is the pressure condition that we experience? A high pressure or a low pressure? What do you think in this region? It will always be very good. It will be high pressure. And here in the hotter region, there is rising parcel of air. So always here you will experience low pressure. Good. Okay. So that is where you experience high and low pressure. But then in between high pressure and low pressure, you will experience that there is movement of air. Air is moving from the region of a high pressure to a region of a low pressure. This movement of air is what we experience as wind. So whenever you would have experienced wind in your day-to-day lives, so that is primarily caused as the air tries to move from a region of high pressure to low pressure always. Okay, so if let's suppose the high pressure is very, very high, in the sense, let's suppose here, assuming the air pressure is 1020 millibar, so it is significantly higher. And let's suppose here the pressure is 950 millibar, so it is very low. So very low pressure means there's a lot of vacancy created near the ground surface, because there is so much air which is rising, there's a lot of vacancy which is present. So when the difference in high pressure and low pressure is very high, the air will rush in with a significant speed and the wind will be strong. So when you experience very strong movement of winds, that means the air is moving from a region of a high pressure to a region of a low pressure. Okay. And when there is a weaker movement of the winds, that means the difference between the pressure is not so great. Okay. So this is what we experience as the wind movement. So wind moves from high pressure to low pressure. Always moves from high pressure to low pressure. Always. Okay. Ankit, your question is exactly the same that what Utsav had asked, and I had replied to that if the cold air sinks, what about the adiabatic process? So, if the cold air sinks, let's suppose there is adiabatic heating, and that is an individual parcel which is sinking. Then, if the temperature increases to such an extent that it becomes warmer, let's suppose the air is sinking, there is compression, and at this level, the temperature becomes similar to the surrounding. It won't sink any further. Okay, it is always going to follow that basic principle. It is not like your portion of organic chemistry that this is an exception where this will happen and that will happen. No, it is uniform all through. So if the air, let's suppose after say in the process of sinking it has become so hotter that it is warmer than the surrounding air, maybe it will rise up from here itself, from the middle portion itself, it can rise up ever so slightly. Okay, so that is basically the aspect of air circulation. Is that understood, Ankit, about the process of adiabatic compression, or is there a doubt which prevails? Okay. Gaurav, why in summer we have low wind movement? From where are you basing this judgment? Generally in summer you will experience very high wind movement. Is it that in winter you experience high wind movement, or is it that in the winter you feel that wind because of temperature? See, always wind movement, at least in India, is very high during the summer months. It is these winds during the summer which brings us monsoon rains also, right? The thunderstorm events, etc., that you experience in the summer. What is that? The stronger wind movement. It is in fact in winter when the almost the entirety of the country experiences a kind of a high pressure where you have almost negligible wind movement. Okay, so yes, LP here is low pressure. Let me write it down. So it is not the case, Gaurav, that in summer you don't have wind. You have rather very strong movement in summer, wind movement in summer. But the thing is that that wind is also warmer, right? So you don't expose yourself to that wind. And in winter, even if there is the slightest of breeze which is colder, you feel that it is very strong wind which is moving, but it is not so. If you take a look at the sheer intensity, the velocity of the wind, always on an average, at least in India, stronger during the summer times. Okay, so low pressure. Yes, Sridevi, that is correct. Adiabatic heating is not as much as the ground surface heated through advection. Absolutely true. Adiabatic heating is never to that great extent. Adiabatic heating is not very efficient as well. Okay. Now, That is about why and how the process of air circulation does happen and does take place. Now, after this, let us understand the different types of pressure or different conditions due to which you have the rising air, which can create low pressure, and sinking air, which can create high pressure. So, one of the important factors which leads to that pressure change is basically temperature. But as I told you, that there can be other factors at play as well. So depending upon the fact that how is it that you have the creation of a high pressure or a low pressure, or how is it that a rising air column or a sinking air column has been arrived at, you have the thermal and the dynamic pressure zones in existence. So here, when you talk about the thermal pressure zones and the dynamic pressure zones, so basically, when we say and when we talk about the thermal ones, so thermal, this is pressure zones created due to heating and cooling of land. So, heater leads to heating of where? Heating of the ground surface. Heating of ground surface will lead to rising air column, and that rising air column is going to attribute to a low pressure. Or let me write low pressure completely. And then colder areas, wherever you have colder regions or colder conditions on ground, leads to sinking air column, and that sinking air column induces high pressure. So in this case, both the rising and the sinking air column basically have been induced by the factor of temperature. So hence the pressure zones which are created because of this, that is the thermal pressure zone, because temperature is the key determinant here or the key factor here which has brought about the variation in temperature, variation in pressure. But what about dynamic pressure zones? Dynamic means what? It is prone to change. It is happening due to some movement. So these pressure zones, they get created because of the movement of the wind factor. Okay, so these get created because of movement of wind. Pressure zones get created due to movement of wind. Okay, because the wind is moving, and that creates the section where you have the rising air or where you have sinking air. How? Let us take a look at how that is created. So when we consider this, let's suppose we consider this particular room, whichever room that you are sitting in, let us consider that itself. Now here, let us assume that near the ground surface, you have installed very large fans, okay, on both sides. Let us assume you have installed very large fan setup on both sides. Whichever room that you are sitting in, imagine that room itself. Think about it that near the floor, near the base, you have set fans on the opposite direction and they are blowing air towards you. So as the air basically is given by these, or the wind is given by these fans. So here the winds will converge. But after convergence, what will happen? Will it be the case that this particular wind which is coming and this particular wind which is coming, they will override each other, go towards the against each other? No, because there also continuously wind is coming, here also continuously wind is coming. Will it be able to break the ground surface? No. After the convergence, it will have no other place to go but then to rise up. It gets pushed up. So when it is getting pushed up, so on the ground, what is the condition which is created on the ground here? On this region, what is the condition which is created? Here again, you have a rising air, but this rising air has been created due to convergence of winds, isn't it? So here you have convergence of winds. Convergence of winds. So on the ground surface, what is the situation that it will lead to? Because the winds are converging, it is going higher up. So on the ground surface, what will be the pressure? Will it be high pressure or a low pressure? What do you think? Beautiful. Very good. So see, convergence of winds has created a situation where the air is rising up from the ground. Okay. This has created a situation where air is rising from ground. And what have we seen a couple of slides back? That rising air always causes low pressure, because when you have the air which is rising, the pressure on the ground will always reduce. So this creates low pressure. Is that clear? Or is there any doubt in this? Krishna, Sridevi, Ganesh, I hope this is clear, right? And Shahid, you also. Okay. Now, after this, we come to another scenario. Let's suppose we consider the same room that you are sitting in. The same room that you are sitting in, let's suppose. But this time, we revert the scenario in such a way that we are this time near the ceiling of your room, right? On both sides, we have installed large fans which are going to blow air towards each other. So let's suppose we have installed very large fans in this area. Very, very large fans have been installed in this area, let's suppose. Now, as this will blow the wind towards each other, as the winds continue to move towards each other, now here again, where will the wind go? In which direction does the wind go? Will it overpower each other? No. Will it break away in the sideways manner? There is no space. So where will the wind go? It has got no other place but to get pushed down. Okay. It has got no other place but to get pushed down. So on the ground surface in this region, what do you observe? That the wind gets pushed down, and then eventually from here it will diverge in different directions, right? So the sinking of air in this region, or the upper convergence, in this the convergence is happening, but convergence is happening where? In the upper region. On the ground surface, that has created what condition? So convergence in the upper air has pushed the air down. So on the ground surface, you will experience sinking air. So what kind of pressure you will have? A high pressure, because you have a sinking air, isn't it? So in this case, convergence in the upper region, convergence in upper region What does it do? Pushes the wind down on the ground, high pressure. Okay, you have creation of a kind of a high pressure on the ground in this scenario. Now, this high pressure which is created on the ground scenario, this is something where you will also observe a kind of a divergence of wind, isn't it? That the air is sinking, it is hitting the ground surface, it is getting diverged. That is something that you will experience here. So can we say that the divergence on the ground surface is associated with creation of a high pressure? So in this case, divergence of winds on the ground surface creates conditions of high pressure. Is that understood? Or is there any doubt in this? Please let me know. Clear? Good. So now we have understood what do we mean by pressure. We have understood that rising air will lead to low pressure, sinking air will lead to high pressure. But this rising air and sinking air, they can be created or they can be the outcomes of multiple different factors. So when you have the temperature as a factor, heating or cooling, so heating will create a rising air column, cooling will create a sinking air column. So that can also induce a difference in terms of pressure, right? In the sense that wherever you have rising air column, there you will have low pressure due to heating. Wherever due to cooling you have sinking air column, high pressure. Now, there can also be the rising air and sinking air created due to the movement of the winds. So if the winds, they are converging, they are moving from different directions and they are converging and then they are rising up, then what do we have? Basically, in that situation, as they are converging, colliding and then rising up on the ground surface, you have the low pressure, right? Because here also you have the rising air. If let's suppose the winds are colliding in the upper region and then are sinking and are pushed to the ground surface, on the ground surface you will experience a kind of a high pressure. So that is where the creation and the existence of various different pressure systems, they are in existence. Okay, now just like isotherms that we studied yesterday, you also have the existence of isobars. So what do we understand by isobars? So here again, iso means similar and bar here represents the pressure. So these are the lines which end up joining places, imaginary lines obviously, which end up joining places indicating same pressure. Okay, so the line on a map connecting points having same atmospheric pressure. Okay, that is your isobar. So again, I will ask you the same question. Can two isobars intersect or cross each other? What do you think? Can we have a situation where the two isobars can intersect or can cross each other? Perfect. It will never be able to intersect. It will never cross each other under no circumstance. Why? I'll just give you the answer because few of you have still said that it will be able to cross each other. So understand this aspect, that suppose when we talk about an isobar, let's suppose it is joining places having a pressure of 1010 millibar. Let's suppose this is the isobar of 1010 millibar. Now, if I have another isobar that is 1000 millibar, so that means in the first one, all the various different places on the first isobar will have a pressure of 1010 millibar. And in this, all the places will indicate a pressure of 1000 millibar. That is why they are joined together. But what about this place A? And if it is lying on both the isobars, that means At the same time, A has got the pressure of 1000 millibar also and 1010 millibar also. Can that be possible? Absolutely not. So that is why isobars will never intersect, will never crisscross each other. Okay? So isobars can never cross each other or intersect. Now, yesterday, if you recall, that we had talked about the fact that isotherms and their spacing, that also gives us an idea about the change or the rate of change of temperature. I hope you recall, right? That if the isotherms, rather, if they are very close to each other, that means the temperature is changing very rapidly. And if the isotherms are spaced far away from each other, means the temperature is changing gradually. So similarly, the spacing of the isobars with respect to each other also gives us an idea about the rate at which the pressure is changing in a particular area. Okay, if let's suppose the isobars are very close to each other, that means in a short distance the pressure is changing very rapidly, right? If let's suppose the isobars are very far away from each other, means pressure is changing gradually. How do we take a look at that? With the help of the image, then we will talk about the conclusions of this. So here, observe this. So I hope you are able to observe this particular map image, and basically this is the isobaric representation over the Indian subcontinent in the month of July, that is the summertime. So here you observe that you have the 998 millibar isobar which is there, 999, 1000, etc. Now if I were to consider an area in this region, let's suppose I consider the region from Mumbai, I consider it for a certain distance up till, let's say, the region of Mangalore on Karnataka coastline. Now, in that small distance, the pressure is changing from 1004 millibar and it is coming to 1008 millibar. So, in that distance between Mumbai to Mangalore, the pressure is changing by 4 millibar, right? Let's suppose I consider this almost a similar distance over the Gangetic plains or the northern plains. So if I were to consider this here across the same distance, almost, okay. Or if I were to this time consider even a larger distance, let's suppose from Rajasthan all the way till Jharkhand or West Bengal. Now here, the pressure is changing by how much? It is changing from 998 to 991, 999. So it is changing by 1 millibar, right? So the isobars, when they are very far away from each other, that means when the spacing is very far away from each other, means that the pressure is changing very slowly. But when the isobars are placed very close to each other, means the pressure is changing very quickly, right? So the spacing of isobars, that how is it that the isobars are arranged, whether they have enough spacing between them or not, that gives us an idea about whether the pressure is changing rapidly or the pressure is changing slowly. Okay, so here when we talk about this, spacing of isobars or spacing between isobars give an idea about the rate of change of pressure, the rate at which pressure is basically changing. So here I will depict it in a simple image also, so that it is easier for you while you guys revise. If I consider two places, let's assume two places of the similar dimension, where let's assume the width is 50 kilometers or 100 kilometers of that area. Let's name this A, let's name this B. Now, if I were to talk about the isobars here, let us assume that we are talking about the isobars. Here in A, I have 999, 998, and so on. 997, 996, 995, 994, 993, 992, 1, 990, 89, 88, 87, 86, 85. Right? On the other hand, let us consider a situation here where we see that the isobars in this region have 999, 998, 997, 996. Now, if I talk about the change of pressure in both these scenarios, so in the first scenario, that is in the case A, within the span of 100 kilometers, the pressure is changing from 999 millibar to 985 millibar. So you have a variation of close to around 14 to 15 millibar, which is experienced in this, right? So within that span of 100 kilometers, the pressure is changing by almost 14 to 15 millibars, right? Whereas in the second case, in the same distance of 100 kilometers, the pressure is changing by how much? From 999 to 996, right? So a matter of 3 to 4 millibars. So the rate at which the pressure is changing, that can be understood or depicted by the spacing of the isobars as well. If the isobars are very close to each other, that means the pressure is changing very rapidly and very suddenly. If the isobars are far away from each other, that means the pressure is changing gradually and very, very slowly. That difference in pressure from one end to the other, that is what is gradient of pressure. The gradient, basically we have seen gradient in geomorphology also. What is gradient? The difference of sorts. So here this is your pressure gradient as it is referred to. So isobars, when they are very close to each other, isobars when very close to each other, pressure is changing rapidly. Okay, the pressure is basically changing very, very rapidly. So that means the gradient is what? A kind of a difference between different areas. So the gradient of pressure from one end to the other end is going to be very, very high. And the isobars, when they are far away from each other, means the pressure is changing very slowly and less as well. So that means the difference in pressure across two ends is less. Gradient is less. So here isobars when far away from each other, pressure changes very slowly. Is this portion understood or is there a doubt? Ridanka, is that understood now? And Shahid, when air converges At that moment, at that region, air density increases suddenly and it should increase pressure. Then it may the region of high pressure, but condition due to air rising, it is low pressure. It is low pressure because see, when the air is converging, the air is accumulating and eventually air is moving where? Air is moving upwards. So always in that case, when the air is moving, it is rising up, it is moving upwards. So on the ground surface, what do you have? Please understand, it is not the case like you accumulate certain bricks, that let us accumulate the bricks, then we will send it upwards. No, air is continue. It is like fluid. Air, the property of air, when you have to study it, it follows the very simple principles of fluid mechanics or fluid dynamics that you would have studied, such as Bernoulli's principle, etc. It follows very similar principles as a fluid mechanics. So when the air moves up or the air is coming towards each other, it basically has to rise up. It cannot go any other place. So on the ground surface, taken on an average over a time period of maybe 1 day or a few hours, always on the ground surface, you will experience a kind of a low pressure. Okay. Now, Ganesh, why isobar miss in the northwest region? Isobars are missing in the northwest region. Where? Uh, why isobar miss in northwest region? It is not missing. It is basically indicating that in this entire area, the pressure is almost consistent. In this entire area, the pressure is almost consistent. That is represented by the isobar. It is not missing. Jaswant, how will we measure the isobars? You don't measure the isobars. You measure the pressure. You measure the, just like how you measure the temperature, similarly you measure the pressure as well, right? So not in the same manner. Obviously pressure is measured by the barometer. I hope we are aware what is the basic of a barometer. So here what is actually done is you have a large installation, not a very large installation oftentimes, but you have a kind of a large vessel, and on that large vessel you keep an inverted cylinder which has got mercury in it, right? This is the basic principle of a barometer. Again, something I expected you guys to be knowing about, but nonetheless, here you have that barometer. Okay, so this is filled with a kind of a mercury column in general. Now the atmospheric pressure which is exerted, the air pressure which is exerted on from top, that air pressure induces a rise in this cylindrical mercury column, and that has got readings or measurement. So accordingly you come across that, okay, this is the pressure. If the air pressure is very high, that means the pressure here will push more into this column, so it will rise even further. If the pressure is low, that means the pressure is low means that there will be less force exerted here, so the rise in mercury column will be less. So like that you measure the pressure in various areas, and accordingly, the once you have the mapping of the pressure of different areas from different weather stations, you join those with an imaginary line, that is the isobar. Okay. Golapalli, once again about A and B. Okay. What do we call gradient in terms of pressure? Akshay, it is called as pressure gradient itself. We'll come to pressure gradient again. So here, understand this, that isobars are basically representation of the kind of pressure readings across, and it helps you understand the pressure distribution in different areas. Now, these isobars, depending upon the ground realities of temperature, wind movement, etc., The pressure can be changing very rapidly from one place to another, or the pressure can change very slowly from one place to another. So here, the isobars, their spacing will always help us understand the kind of change in pressure which is experienced. So when the isobars, so in the first one, you see that the isobars are very close to each other, which means that each of, or in this area, pressure is changing very, very rapidly. So at one end here, you had the pressure of almost 999 millibar. And by the time that you travel 100 kilometers in this region, the pressure can reduce to almost 985 millibars. So that is something that we can depict by the spacing of the isobars. So when you draw the isobars in any area, I will show you the isobars here as well. Observe, this is the isobar over North America. Now, wherever you have the isobars spaced very closely with each other, means what? In this area, the pressure is changing very rapidly. When they are very far away from each other, means what? In this area, the pressure is changing very, very slowly. So the spacing between the isobars, that also gives you a clue and an idea about the rate at which the pressure is changing. Okay. As the convergence of Golapalli, I hope that is understood. Uh, Utsav, as the convergence of air at the bottom creates pressure, high pressure everywhere, and above that the pressure is low, so it rises up. Can it be the reason why air is moving upwards only? No. In some extent, in certain cases, yes, but understand, Utsav, the primary reason for this is that the wind is continuous. That is why I told you that you install a fan. In that example, I gave you the fan example. I did not give you the example that two pockets of air is coming, they are converging. Where do they go? The very reason why I gave you the example of the fan means the fan continues to move the air together, continues to push air against each other. In that situation, the air has got no other place, virtually no other place to go. Yes, there will be an intermediate pressure difference. What you have said is also correct in the local region, that in the intermediate region, there will be a pressure gradient which will be in existence, which can lead to the rise. But eventually, it is the continuous movement. Imagine if you had a situation where you had one parcel or pocket of air coming in, another pocket of air coming in, and both of them then not being reinforced by further wind movement, both of them would basically converge. They can stay in the same region for a long period of time. They won't rise up at all. But if it is a continuous wind movement, then you have no other place but you are forced to rise up. So that is what creates that low pressure on the ground. Okay. And in isotherm during winter in water, it will always move towards. Likewise, is there any relationship in isobars? Not significantly, no. And Abhishek, is rising and sinking of air always associated with low pressure and high pressure? Always rise of air will create a low pressure. Always sinking air will create a high pressure on the ground. Okay? Yes, Pranay, that is correct. Gaurav, which region have more wind movement? Isobar at high distance or isobar at low distance? We'll come to it. We'll come to it. Okay, till now, any other doubts that you have? Feel free to ask. Don't worry. Any other doubts? No? So I assume till now this portion is clear. Akshay, I already told you the difference in pressure or the pressure gradient, that is what we are coming to now. Okay. So now we come to the aspect of pressure gradient. Pressure gradient is what? It is basically the change in pressure with horizontal distance. That is termed as pressure gradient. From one region to another, as there is a difference in pressure, to what extent is that a pressure difference? That is the gradient of pressure, right? For example, take the simple example, always I tell you that take the example of water in this case. Now, if ever you have tried, obviously you would have tried, take a jug of water and take a glass. Now, pour it in the glass. Water will come down with a velocity. But when will the water start pouring down? When you lift the jug above the level of the glass, that is when the water will start pouring down. So you are providing a height difference. In that height difference, the water will flow. Let's suppose I lift the jug to a certain height, significantly greater height, and then I start pouring it down. Then what happens? Water will come down with a much greater velocity. Let's suppose I take the jug to the first floor and then I start pouring down the water. Water will come down with a much greater velocity. So, greater the difference of height, greater is the speed of water movement, right? So, that is the height gradient, which is in a way influencing the rate at which the water will be moving. Something very similar also pans out when we talk about the pressure gradient. Pressure is what? The abundance of atmospheric particles, the weight imposed by the atmospheric particles on the ground surface. That is what do we understand by pressure. So in a region of high pressure, now high pressure can be comparative, right? For example, in certain areas, even 1015 millibar can be a very high pressure. In certain areas, in comparison, even when we talk about 1020 millibar, that can be a very high pressure. So that high pressure, that is very subjective in nature itself, right? So let's suppose if we have a region of high pressure where there are a lot of various different particles involved, lot of various different. So high pressure means there is a lot of particles, there would be sinking air, that is why there is a kind of a high pressure. So here you have a lot of various different particles, and in the region of low pressure you have almost negligible presence of any particles at all. So what do you observe in this case? The winds are pushed from the region of a high to a region of a low, or the particles, they move from a region of an excess to a region of a deficiency. So pressure gradient also ends up determining the quantum of wind movement, in the sense the amount of wind that will move, the velocity at which the wind will move. Just like in the case of if the water example, if you pour water from a very great height, it will induce a higher velocity. If you pour water from a lesser height, the movement will be slower. Similarly, if the difference in pressure between two areas is very, very high, the associated wind movement will also be very strong. And in case the difference in pressure in two areas is very less, very feeble, the wind movement will also be very less. So, here, when we talk about the aspect of pressure gradient, so basically, it is the difference between the high pressure and low pressure. If the difference between the high pressure and low pressure is very high, that means the high pressure may be 1020, low pressure may be 950. That is a very high difference. So in that case, the wind movement will be very strong, right? Because you have very surplus particles and a lot of deficiency in one region. So there will be a rushing in. So always high pressure gradient is associated with very strong wind action. So in case here, if the difference is very large, you have very strong wind movement. Okay? You will experience a kind of a very, very strong wind movement. And then, if the difference is very small, the difference between high pressure and low pressure, if that is very small, then obviously the associated wind movement will also be weaker. If the difference is very small, in pressure or in between high pressure and low pressure is very small, weak, weaker wind movement. And how do we get to know about the pressure gradient? Just by looking at the map, we can understand it by taking a look at the spacing of the isobars. Okay, so in this case, if I take you back into this image, out of A and B, where do you think that the pressure gradient is high? A or B? Where do you think that the gradient of pressure is very high? Clear? Himanshu, Sridevi, Priya, and Ridanka and Soni. Please let me know why is that the case. Kindly let me know why is that the case. Until that point of time, I will answer the question asked by Anuranjan. Anuranjan, your question was that why isobars do not intersect each other. See, isobars are what? Places indicating the similar pressure. So, when you have isobars of or all the places having the same pressure, they are joined by these isobars, right? So, let's suppose I have an isobar here. I'll try to find an empty space. Let's suppose I have an isobar here. So, or before that, this is A having 1000 millibar, B having 1000 millibar, C again having 1000 millibar. So if you join an isobar, or if you join this by an imaginary line, this will be the isobar. So this can be a 1000 millibar isobar. So that means all the places on this isobar which lie on this isobar will have a pressure of 1000 millibar. That is why we are joining this with the imaginary line. Okay. So if I have a 1000 millibar isobar here, that means all the places on this represent a pressure of 1000 millibar. Let's suppose another isobar intersects here, that is 990 millibar isobar. So that means all the places on this 990 millibar isobar will have that much pressure. What about this place here? Let's name this place as O. At O, what will be the pressure? Will the pressure be 1000 millibar or will the pressure be 990 millibar? What do you think, Anuranjan? So obviously, you cannot find out what will be the isobaric or what will be the pressure here. Why is that the case? Because ideally, if I talk about this region A, it will have 1000 millibar. If I talk about this region C, it will be 990 millibar. But O at the same time, will it have 1000 millibar or will it have 990 millibar? At the same time, a region can have only one pressure. At the same time, a region can have only one temperature. It can have only one condition of pressure. It cannot be the case that Delhi right now is experiencing 25 degrees Celsius also and 35 degrees Celsius also. It cannot be the case. Either it is 25 or 35. So, similarly, at any point of time, any place will experience the same kind of pressure. So, if you have the pressures or the isobars intersecting each other, means that place is experiencing two pressures. That cannot be the case. Hence, isobars, isotherms, etc., they won't be able to crisscross each other or they won't be able to intersect. Okay, I, I hope that is understood. Is that understood? Okay. See, only if it is understood, then take a call. Otherwise, don't simply try to ignore the problem under the carpet. That is not helping yourself at all. Okay. Shiva, distance will also determine. And so I had asked Priya and Sony and Ridanka about why is it that the pressure gradient you are saying is higher in the case of B. So the pressure from A towards B will be experienced. No, this entire sample is A, my dear friend. This entire sample, this region is B. Always understand When the isobars are placed very close to each other, that means the pressure is changing very rapidly. Within this 100 kilometers, the pressure in A is changing from 999 millibar to 985 millibar, almost a difference of 14 millibar within a span of 100 kilometers. That means the gradient of pressure in these 100 kilometers is by 14 millibars. Whereas in this case, in the second case, the gradient of pressure in that span of 100 kilometer is only by 3 to 4 millibar. So where is it? What is gradient? Gradient is the difference between the high pressure and the low pressure in this case. So here, where is it that the gradient is higher? Gradient is higher in the case of A, right? Where in the short span or in the short distance, it is a short distance of 100 kilometer, the pressure is changing by 14 millibars. In case of B, in the same span of 100 kilometer, the pressure is changing only by 4 millibar. So always the gradient will be higher in the case of A. Okay, is that understood? Okay. So this is basically what is understood by the pressure gradient. That is the difference between high pressure and low pressure. If that difference in high pressure and low pressure, think about it. Look at this particular image on your screen. If you observe this particular image, here you would be observing this is a region of high pressure. This is a region of low pressure. Low pressure means lesser particles. High pressure means larger number of particles. If let's suppose the number of particles here keeps on increasing, that means the high pressure keeps on strengthening. Here you will have a significant surplus in this region. And here you have deficiency. So the air particles will move from a region of surplus to a region of deficiency. So that induces what is referred to as a wind. So greater the surplus, greater will be the movement, isn't it? And when do you have a greater surplus? When the difference between high pressure and low pressure is very high, that means there is a greater surplus at the region of a high pressure and the greater deficit at the region of low pressure. So that means the wind movement associated will be very, very strong. Okay, so always a higher pressure gradient is associated with a stronger wind movement. Always a low pressure gradient is associated with a weaker pressure gradient. Okay, I hope that is understood. Now, then we come to the various different factors which influence the velocity and the direction of the wind. Basically, when the wind is in motion, and you would have experienced this also, that it is not always every day that the wind comes with the same velocity. Sometimes it can be as gentle as a breeze with a speed which is very slow, which is very pleasant. And when you stand up to that wind, it is a pleasurable experience. Sometimes it is so very strong. It is basically something which is not even bearable or tolerable. So the wind speed keeps on varying. The direction of the wind also keeps on varying. So, based upon what factors would you observe this? So, that is where we come across the various different factors which influence not only the movement of the wind, but also the direction and the speed that the wind gains. So, broadly, there are three major factors which are important here. Which are those three major factors? First of all, when we talk about the horizontal wind, that is moving across the surface, now the three factors are the pressure gradient force or the force induced due to the difference in pressure, the Coriolis force, which is induced due to rotation of planet across its axis, and then you have the frictional force, that as the wind blows across the ground surface, it will experience various forms of resistances across, let's suppose, from the trees, from the various different types of land formations, etc. It will experience resistances. So that also induces a kind of a variation in the wind velocity. So these are the three major factors which will always impact the movement and also the direction of the wind. So, in addition to that, the gravitational force is always prominent. Gravitational force is also responsible because it is a gravitational force which ensures that the wind basically is on the ground. It doesn't simply is lost up and rises up. So here Let us understand each of them: pressure gradient force, the frictional force, and the Coriolis force. Let us understand the nuances and the properties of each one of them. And let us understand how will they influence the wind movement. So first of all, we start with the pressure gradient force. In simplest of the terms, basically the force which is induced due to the gradient or the difference of pressure, okay, between one place to another place. At what rate is the pressure changing? That is what is pressure gradient. And whenever there is a pressure gradient, it will induce a movement of particles. As we saw in this case, it will always induce a kind of a movement of particles. And that movement of particles is induced. It is referred to as a force which has been created due to the difference in pressure. Hence, it is a pressure gradient force. Okay? So, the rate of change of pressure with respect to distance is the pressure gradient, and basically that induces a wind movement, that induces the movement of particles from one region to another, and that is what we regard as the pressure gradient force. So higher the difference of pressure, how do we understand that there is a very high difference of pressure in a small region? By the spacing of isobars. Always it is understandable. If the isobars are very close to each other, means the wind is or the pressure is changing very suddenly. If the isobars are very far away from each other, means the pressure is changing very slowly, very, very gradually. At the end of it all, always remember the same basic, that the wind always blows from a high to a low. So the wind movement that is associated will be from a region of a high to a region of a low. So winds always blow from a high to a low, means high pressure to a low pressure. So observe here. This is the isobaric representation or the pressure variation representation in the region of North America. Now this is the region of a high pressure. As you can observe here, in this entire area, the pressure is 1036 millibar as represented by this isobar. Now here, you have a spacing between the isobar is significantly larger. That means the pressure is changing very, very slowly overall, right? The pressure is changing very, very slowly. So then you have 1028, etc. Here you have the absolute low pressure of 988 millibar. Okay. Harsh, your slide is all messed up. Please correct it. Which slide are you talking about, Harsh? Please specify. And then we proceed. Please let me know which slide are we talking about here? And where is it that you seek a correction? Okay. Meanwhile, as you type, we proceed further. But I expect an answer immediately. Okay. So here, see, when the isobars are far away from each other, that means the pressure is changing very slowly, means the pressure gradient is low. When the pressure gradient is low, the wind movement will also be slower. The wind movement will be slightly significantly slower, isn't it? So here you will find that there is a kind of a shallow gradient. Shallow means less gradient, and shallow gradient is associated with weaker winds, very weak winds which are present. And then you have here the isobars are very close to each other, immediately next to each other. So that is a steep gradient. That means the pressure is changing very rapidly, very suddenly. And then there you will have strong winds. Okay. So that is where you will find basically that the wind movement, the speed of the wind associated, that is always going to lead to the variation, or that is associated with the difference in pressure. So greater the difference between high pressure and low pressure, stronger is the wind movement. Lesser the difference between high pressure and the low pressure, weaker is the wind movement. I mean the front display view. The arrow became large. Which arrow are you talking about, and which slide exactly are you talking about? Specify. I don't want random shooting into the air. This is not a political rally that we are a part of. Siddha, what type of questions from this topic can be asked in the mains and prelims? So you can expect a question in prelims about the very basics of the pressure gradient force, etc. Why is it that the creation of high pressure and low pressure? And then basically the majority of the questions will be associated with the factors of vegetables, trade winds, etc. But for understanding them, you need to have a clear conception of these areas. Okay. Um, in this case, what is the direction of the wind movement, Priya? Do we have a shallow gradient each side? So, see, wind will always move towards the lowest of the pressure. Wind doesn't know what is north, what is east, what is west, with what is south. Wind always will move from high to low. So, this is high pressure, this is low pressure. Here on the other side, where there is low pressure, you don't have an idea. So, the wind will always have this direction. But in this area, that now from this point A to this point B, wind will not be moving at the same speed, right? So in this region, the wind will be moving very slowly. Why? Because the pressure gradient is less. In this area, the wind will be moving very quickly. Why? Because the pressure gradient is fast. Okay. Shallow basically means that here, when we talk about shallow, shallow means less. Less. So shallow gradient here refers to, when we talk about shallow gradient is basically pressure gradient is less. Steep gradient is pressure gradient is very high. Is very high. We do know that the wind velocity is associated with the pressure gradient. So if you have the wind velocity, which is basically, if the pressure gradient is very high, that means the wind velocity will be strong. If the pressure gradient is less, means the wind velocity will be lesser. So here, if the pressure gradient is less, that is in this area, the wind velocity, it is the weaker winds which are associated here. That means slower moving. And suddenly, as the pressure changes rapidly in this region, wind velocity will pick up quite significantly. Okay. Gaurav, what are trade winds? My dear friend, please have patience. We'll cover that. And Parshuram, the movement of pressure, the movement. Okay, so Parshuram, if I am trying to gather your question correctly, it is about the, are you asking that the isobars remain consistently in this position or not? So the isobars, they can change by the hour. Just like in the case of isotherms also, you can have the change of temperature by the hour, by the day also the temperature will change, right? So whenever, suppose for today, if you have to have the isobaric representation, it will take a kind of a 24-hour average of that area. What was the pressure experienced, let's suppose, in Delhi during the day, during the evening, during the night, and along accordingly you draw out the average. So isobars, they are prone to change from one season to another, from one region to another, it changes. Was that the question, Parshuram, or was it something different? And do we have to draw the exact diagram as shown over PPT in the same topic question? We'll come to it. Mains question would be directly or on concept, or it can be an application. It will always be an application based question. Okay. It won't be the case that describe the difference between pressure gradient express. No, not that kind of a mains question. Mains question from this area will always be associated with the kind of permanent wind systems, the pressure zones, etc. but that is what we are leading to. So these are the basic concepts you need to understand, so that the pressure zones, the movement of the wind, etc., that is understood very clearly. If the pressure changes rapidly, then movement of wind is very fast. Yes. Pranath, there is also change in temperature and pressure in local areas. Absolutely, yes. Okay. So now we come to another force which ends up determining the direction that the wind will take. Before that, do you need a 10 minutes break in order to get your mind in order to refresh yourself, or can we continue? Okay. Does it mean when the wind moves from shallow to steep gradient, as the wind enters into it experiences succession kind of, it speeds up, in simpler words? Sri Devi, a high pressure, low pressure gradient, low pressure, high pressure gradient. Not always, Sri Devi. You cannot have that conclusion. See, the if you talk about the region of Himalayas, for example, or the northern plains and the Peninsula Plateau. Now, from one region to another, let's suppose the northern plains represent a very low pressure because of heating. It represents 950 millibar. And the region in, let's suppose, Bangalore represents 1000 millibar. From 1000 millibar to 950 millibar, that change can happen in multiple ways. It can also happen, if I take you back to the image of isobars for a brief moment. Observe here, in this case, in this map, understand this. Here you have 998 millibar, this one around Chandigarh, 998 millibar. Here you have 1006 millibars, this one. Now, ideally, this is comparatively a high pressure, this is comparatively a low pressure. So here you will have a steeper gradient because the isobars are very close to each other. If let's suppose the wind is coming from here, it will have a shallower gradient, right? So it can vary. It depends on various circumstances of temperature, of movement of wind in any particular area. It is something which depends on that. Okay, I hope that is understood. Okay, so should we continue or we take a break, guys? Okay, let's do one thing. Let's not ponder too much over it. Let's take a break and we'll be back in around 10 minutes and then we continue. But I want you guys to be alert after you come back. So, whatever you need to do it. Be alert when you be back. Okay. A confirmation about the audio, please, guys. If the audio is clear and available, good. Uh, Priya, I'm not that much able to connect in geomorphology chapters, but in climatology, it seems like connected so far. So, in this case, can I skip geomorphology chapters? How much will it affect? Please don't skip it at all. See, as of now, while studying, fair enough. Right now, concentrate on the portion of climatology. But UPSC, for example, this year also had a direct question asked in the both mains as well as prelims from geomorphology. Last year also it had a direct question asked from that. You cannot afford to skip. So it will be very similar to the fact that I like polity better. Can I skip the subject of economy? You cannot afford to do that. It will be at your own risk. Climatology is certainly more important for civil services, but geomorphology is not irrelevant either. So take your time in geomorphology, start with the basic portions. And in fact, I would rather argue that climatology, in that the building of concepts, the interconnectivity is there, but it becomes much more complicated going ahead. Geomorphology is not at all complicated. Geomorphology operates with a very simple mechanism. Earth's formation, residual heat in the inside, leading to the movement, and that movement is leading to changes on the ground surface. That is it. So once you are able to formulate that, and in the module coverage, the second and the third module, if you are able to digest, geomorphology is also digestible. Okay. But as of now, if you are finding it difficult, do it at the end. Once you have gained an overall perspective about the portion of geography, second time when you visit it, it becomes automatically easier. Okay. Now we come to the Coriolis force. What is this Coriolis force? Where does this act? Why does this act? And basically, how does it influence when we talk about the wind movement? So, Coriolis force is a kind of an apparent force. It is referred to as an apparent force, not a direct force. Why? Because Coriolis force comes into action due to the rotation of the planet Earth. Okay. Had the planet Earth not been rotating on its axis, let's assume a situation where the planet would not be rotating, Coriolis force would not have been present. Coriolis force would not have acted at all. In this case, the Coriolis force does act. Now, on any object which is moving across various different parts of the planet, any object which is in motion between one region to another, you do experience this Coriolis force. So, even when you observe the aircrafts flying, the airplanes flying, they also experience the Coriolis force. When you launch a missile from one region, target it to another region, there also you experience the Coriolis force, right? So the Coriolis force is basically purely because of the rotation of planet Earth. Now, why does this force act? What is this force about, and what is its impact? So any object which is moving freely in the northern hemisphere tends to bend to the right due to the Coriolis force. Any object, okay, any object which is moving to the left or which is moving in the southern hemisphere tends to bend to the left. So the Coriolis effect describes the pattern of deflection taken by objects not firmly connected to the ground as they travel around the planet, right? And this is based on the principle that we covered in the first module. If you recall, in the first module we had talked about the fact that as the planet rotates on its axis, different places will always indicate different rate of motion, or a different speed of rotational motion will be expected and experienced at different regions, right? I hope you remember that, where we observed that the speed of rotation at different places will be very different. Any of us who doesn't recall that, or any issue in that? Where is it that the speed of the Earth is fastest? The rotational speed is the fastest. In which part of the planet is the rotational speed the fastest? Very good. Equator. Right. And where is it that the speed is slowest? Almost negligible. Almost zero. At the region of the poles. Beautiful. So this difference in speed, that induces the bending. Now, bending is observed in the air movement, aircraft movement, missile movement, or even for that matter in oceans. When you have ocean currents and currents of oceanic water moving from one region to another, there also you will experience this kind of a bending force or the bending event coming into action. So here, let us take a look at it, that why this happens. Okay, so the key to the Coriolis effect lies in the Earth's rotation. Specifically, Earth rotates faster at the equator than it does at the region of the poles. While at the region of equator, basically there the speed is close to around 1600 kilometer per hour. At the region of the poles, it is almost around 0 kilometer per hour. So that means different speeds of rotations are in existence. So speed of rotation is fastest at equator, then it reduces as you slightly move towards the poles, and eventually it will be zero at the region of the poles. Now, that difference in velocity means any object which is moving from equator, let's suppose, towards the region of the poles, rather than reaching its destination, it will reach somewhere else, right? Any object which is moving like this, or from the region of the poles to the region of equator, rather than reaching its destination here, because of the different speed of rotation, it will end up reaching somewhere here. So that is the Coriolis effect. Why does this happen? We will understand that with the help of a very simple example, analogy of sorts. That is what we will use to understand this. So here, when we talk about this, first of all, we take the example or the simple car example here. So let's suppose you have two cars. This is about that how when an object moves between areas indicating different speed, they will observe a deflection. That is the entire crux of the Coriolis force. Let me write it down here also. So, due to different speed of rotation as an object moves between regions rotating at different speeds, it experiences deflection. Okay, that experiences a kind of a deflection. Now here, when you think about it, let's suppose we consider three different scenarios. We have two different cars here. Let's name this as car A. Let's name this as car B. Let's assume both of them are moving in the same direction with the same speed of 40 kilometer per hour. Okay. Now, if you observe a kind of, let's suppose, an object which is thrown from A to B, okay, an object which moves from A to B here. Now, if you have two cars which are moving at the same speed, someone from first car throws a ball to the second car, let's suppose, then the second person in the other car, will that person be able to catch it, or will that person be able to get it? So here you can relate it with your day-to-day examples as well. You would have seen many, or you yourself would have done this mischief as well. Many of the times you would observe that you, your friends, all of them, you decide that, okay, all the conversation we'll have on the road itself. So we'll move the motorbikes or the scooters or the cars or the vehicles at the same speed. So for you, you are basically moving at the same speed with your friend. So for you, your friend appears to be static. While for a person on the road, you are moving at a speed of 40 kilometer per hour, but with respect to each other, because you are moving at same speed, you are basically static. So a person who throws a ball from A will be caught by the person at B very easily, isn't it? Because both of them are moving at the same speed. But if we consider another scenario here, let's suppose I have A, let's suppose I have B. Okay, A, B. A is moving at 40 kilometer per hour. B is moving at 140 kilometer per hour. Now you throw a ball from A to B. Now what do you think? Will the ball be caught by the person in B? Will the ball fall ahead of car B? Or will the fall behind the car B? What do you think will be the scenario in this case when A is moving at 40 kilometer per hour and B is moving at 140 kilometer per hour? Will the ball be caught by B? Will it fall ahead or will it fall behind? Right? Simple. Because here, by the time the ball reaches this place, B would have raced somewhere significantly ahead, isn't it? B would have moved maybe here by that time. So for a layperson standing on the road, for a layman standing on the road, from that person's perspective, if you ask, that person will tell you that actually the ball fell behind B, right? So in this, can we have our inference? An object moving from a slower speed to a faster speed falls behind. Right? Here also, object moving between places of same speed does not deflect, doesn't experience deflection. Right? We can have this conclusion because both of them are moving at the same speed, so B will be able to catch the ball. The third scenario. The third scenario is where we observe object A, object B, okay, this is A, this is B, here. Let's suppose this time this is moving at 140 kilometer per hour. The second one, B, is moving at 40 kilometer per hour. Again, you throw the ball. Now this time what will happen? Will the ball be caught by B? Will the ball fall ahead of B? Or will the ball fall behind B? What do you think in this situation? Very good. It will fall ahead, right? Because basically, when you are moving in the car at 140 kilometer per hour and you have the ball with you, ball will also have some part of that forward motion. So when you throw the ball will have a trajectory somewhat, and by that time, B would not have reached here. So in a way, the ball would fall ahead, right? So object moving between a faster speed to a slower speed falls ahead. Okay, it falls ahead. So, with these three conclusions, let us try to solve the mystery about why is it that the objects in northern hemisphere they will be bending to the right while they are moving, and why is it that the moving objects in the southern hemisphere they will be bending to the left. So here, if you take a look at the entirety of the planet, for example, let's suppose we consider the entirety of the planet here. Now we know that the shape of the planet is such, it is slightly flatter at the poles, but it is bulged around the region of equator, the geoid shape that we have. So here, if I have to, let's suppose, think about drawing the equator. What we will do is, we will also demarcate the areas immediately above and below equator as well. So let's assume this is 5 degree north. Let's assume this is 5 degree south of equator. Let's make the equator with a kind of a solid line so that there is no confusion. This is your equator. These are your poles. Now, here, when we talk about the speed of rotation, can I assume that the speed of rotation of this region, 5 degree to the north of equator and 5 degree to the south of equator, will I be correct to assume that the speed of rotation of at equator and these three places, that will be largely consistent? Right? Because the radius in these areas is going to be almost similar to the region of equator, right? So can I assume that the speed of rotation at the point 1, at the point 2 will be similar to that of equator? Fair enough? Any doubts in that? Good. So speed of rotation at 1 and 2 is almost similar to the speed of rotation at equator. Of rotation at 1 and 2 is similar to the speed of rotation at equator. Okay? Now let us think about how is it or why is it that the deflection will happen. So let's assume we keep a place or we talk about a place here that is A. We talk about a place here B. We talk about a place here C. Now an object, if it is moving from A to B, its destination is B. So can we say that this object is moving from a slower speed of rotation area to a faster speed? We can say that the object is moving from a region of a slower speed to a region of a faster speed. What have we taken as a conclusion from there? That an object moving from a slower speed to a faster speed, that always tends to fall behind, isn't it? So the object, rather than reaching B, will reach somewhere here, because equator is moving at a much faster speed. So this will fall at B dash. Now what is this deviation? This is the rightward deviation, isn't it? Whenever you have to take a look at whether it is leftward or rightward deviation, always try to place yourself at the source or the origin and think about it that you are looking towards the direction of movement. So your right will give the rightward deviation, your left will give an idea of the leftward deviation as well. So in this case, this is what? A kind of a rightward deviation, right? And then let's suppose conversely, let's suppose from B, an object is trying to move to A. Now from B, if an object is trying to move to A, basically it is moving from a faster speed to a slower speed, right? So from a faster speed to a slower speed, we have seen that the object falls ahead. So here, this will fall ahead here, A dash. What is this deviation? Rightward. So you have rightward deviation, in the northern hemisphere. What about the southern hemisphere? The same principle will be followed. So let's assume that you have the movement from C to B. B is the destination. Again, C is rotating at a much slower speed, B is rotating at a much faster speed. We know that the object, when it moves from slower to faster, it basically falls behind. So rather than reaching B, this might reach somewhere here, maybe B double dash. Now, what is this deviation? This is a leftward deviation, isn't it? Similarly, let's suppose from B to C, the object is coming. So faster to slower. So it has to fall ahead. Please understand, rotation is continuously happening from west to east, right? So it will end up falling somewhere ahead. C dash. What is this deviation about? This is again a leftward deviation, isn't it? So objects in the northern hemisphere, they will always have a tendency to bend to the right. Object in the southern hemisphere will always have a tendency to bend to the left. That is what you observe in the case of or due to the Coriolis force. Now, why is that bending or deflection happening? Because of the difference in speed between different areas. From one region to another, as you encounter different speed, that is why this bending is happening. If, let's suppose, we consider the region of 1, 2 and the region of equator. So let's suppose an object is moving from 1 to 2. Now, the speed of rotation at 1 and speed of rotation at 2 is almost similar, that of equator. So what do we have? We have seen that when the speed or is same and the object moves between the similar speed, there is no deflection, no deviation, right? So here, basically, there will be no deviation at all. So that is why around equator, you don't experience the presence or the impact of the Coriolis force. That is why it is said that Coriolis force is absent at the region of equator. So here, Coriolis force is absent. Absent at the region of equator. Okay. It is absent at the region of equator. Now, what about the region of the poles? And again, I will reiterate the same thing, that this bending or deflection is happening purely because of what? Difference in speed. Now, the difference in speed, basically, the speed of rotation at, let's suppose, speed of rotation of the planet here, speed of rotation of the planet here. Now, the speed of rotation at pole is what? 0. This is the speed of rotation is 0. So, here, when an object is moving from any place to the region of the poles, the difference in speed will be very high because the speed of rotation at the poles is absolute 0, right? So the difference in speed from the region of the pole to anywhere else, it will be very, very high. That is why it is said Coriolis force is absolutely higher in the region of poles. It is the maximum around the region of the poles. The intensity, the amount of Coriolis force keeps on increasing from the equator as you move to the poles. At equator, it is 0. Around the region of poles, it is maximum. So when we basically try to conclude this here, when we try to talk about this here, So it deflects the wind to the in the rightward direction in the northern hemisphere. It deflects the wind in the leftward direction when we talk about the southern hemisphere. And here it is maximum at the poles and is absent at the region of equator. Why maximum at the region of the poles? Because the difference in velocity between the pole and any other area will be very high, because the speed of rotation at the poles is zero. So here, let me write it down as well. Difference in velocity between any region and poles is very high. Why? Because speed of rotation or speed at poles is zero. So that is why there will always be a larger difference in velocity. Now here you always also find that the Coriolis force acts perpendicular to the pressure gradient force. What is that? And how does that happen? So pressure gradient force acts between the region of high pressure to low pressure always. So let's suppose here we talk about the northern hemisphere. Let's suppose in the northern hemisphere. So if you have the region of a high pressure and if you have a region of a low pressure, what will be the direction of the pressure gradient force? From high to low, that is the direction of the pressure gradient force. This will be your pressure gradient force. Now we are in northern hemisphere. So in which direction will the Coriolis force be acting? It will be acting in the rightward direction. Coriolis force will be acting in the rightward direction. Right? And that is why the resultant wind that you will observe will be somewhat like this. When we talk about the southern hemisphere, let's suppose, in the southern hemisphere. Now here, let's suppose here you have the high pressure. Here you have, let's suppose, the low pressure. What is the direction of the pressure gradient force here? It will be like this, right? This will be your direction of pressure gradient force. And what about the Coriolis force? Coriolis force will be acting in the leftward direction, or in the leftward direction rather here. Isn't it? This will be your Coriolis force. So the final wind movement will be somewhat like this, the resultant of both of them. So that bending of the wind, that movement or deflection of the wind is purely happening because of the rotation of planet on its axis. And that is what is referred to as the apparent force, that is the Coriolis force. So Coriolis force is significantly important in leading to deflection of the wind, movement of the oceanic water and its direction. In all of those, Coriolis force is instrumental. Now we come to another force, that is the frictional force. Now, when we talk about frictional force, what is frictional force? It is a force of resistance. Resistance offered by what? Resistance offered by the various different things that you have on the ground surface, the trees, the mountains, etc., the various different ground features. So when the wind blows, the wind speed significantly is reduced because of that force of resistance, isn't it? So this is a force of resistance. Force of resistance, always. So when we talk about a region, let's suppose like this, here it has got various different types of features. Let's suppose you have the presence of trees, vegetation, everything in an area. Okay. Now, as the wind is moving, there will be resistance offered by these various different objects, various different types of obstacles which are there in the path of the wind. They will offer a kind of a significant and substantial resistance. But here, if basically the wind, if let's suppose, is moving at a height of 3 to 4 kilometers, then the resistance offered is very less, isn't it? So the frictional force is very high near the ground surface. and it keeps on reducing as you move higher up. That is why at a greater height, the speed is of the wind is faster. In higher altitudes, the speed of wind is faster. You can experience this on the small scale also. If let's suppose you go to a high-rise building and you go to around 20th floor, 21st floor, or somewhere like that, you observe a very strong wind movement, isn't it? And why is that? Because you don't have the obstacles of the houses, etc., near you, so you face a strong wind movement. So that is something which is replicated on the ground surface in the normal wind movement as well. Here you have to understand that when we talk about, let's suppose, the water bodies like seas and oceans, there you don't have this resistance which is offered. There, that force of resistance is almost absent. So, in that case, the wind velocity is substantially going to be much higher. Okay, so that is where you have to understand the role played by the frictional forces to reduce the wind velocity. So over the sea surface, the friction is minimal, so the speed of wind is high. Of wind is very high. Okay, that is why in general, when we talk about the oceans and seas, especially in the southern hemisphere, or in general, you will find that the wind movement in southern hemisphere is much stronger as compared to northern hemisphere. Why? Because the southern hemisphere is dominated by the oceans. That is why around the region of the southern ocean, you will find that, for example, the permanent wind systems such as the westerlies, they are so very famous to make a kind of a noise. When the winds go very strong, they create a kind of a howling noise, almost scary to a certain extent. So that noise is created by the winds, right? So the westerlies in the southern hemisphere, they are known by different names. For example, shrieking 60s, furious 40s, and so on. That is associated with the latitude and the sound that they emit because of the high velocity. So that is the condition of frictional force. Okay. Now, okay, Shiva, is there any relation between the altitude from ground and Coriolis force? Not a direct relation between the altitude and the Coriolis force, but higher the wind or the higher the velocity of the wind movement, greater is the Coriolis force, bending which is observed. Okay, so higher the deflection is more when the wind velocity is high. Okay, so for example, when an object is moving from A to B, it is moving at a very slow speed. Maybe that deflection won't be very much because of the relative velocity. But if it is moving at a very fast speed, it will be decoupling itself from the ground, and that is when the deviation will be high. So as you move higher up in altitude, you will experience a significantly greater amount of deflection. Why? Because of high wind speed. Okay. Is Coriolis effect unrelated to centrifugal force? Yes, it is not related to centrifugal force. Shiva, is that understood? That it is basically associated with the wind speed, not with the altitude. But with increasing altitude, the wind speed will be faster, it will be higher. So obviously, deviation will also be higher. Now, after this, we take a look at the concept of onshore and offshore winds. What do we mean by them? So, when we say onshore winds, these are basically your winds which end up moving from the water body to the land areas. That is the onshore winds. When we talk about offshore winds, what are these? The winds which are moving from land to the sea. Right? So, onshore is basically the wind moving from winds moving. So, imagine if you have a wind moving like this or wind moving like this. Now, this is moving from sea to the land. Winds moving from sea to land. Right? Now, this wind, which is coming over from the sea to the land or from water to the land, it will be laden with lot of moisture, lot of water vapor it will carry because it is coming over from the sea areas. So all that will be dropped on the land in the form of rainfall. So onshore winds will always be associated with the occurrence of rainfall. So this causes rainfall always. Okay, always it will cause rainfall. Whereas offshore winds, let's suppose you have a wind movement like this, or let's suppose a wind movement like this. That is from land to the sea. Winds moving from land to the sea. By the way, this is different from your land breeze and sea breeze that we are talking about. Land breeze and sea breeze, which we'll take a look later in this module itself, that occurs over a very short distance. We are talking about large wind patterns which are prevalent. So this wind, because it is originating from the land, it is drier. Wind is dry as it originates over the land areas. The land regions. Okay. And thereby, it is basically does not cause rainfall. Okay. That is the characteristic that you would observe with the case of onshore and offshore winds. Okay. Now, after this, we come to the portion of air circulation. Air across the entirety of the planet, that is continuously in motion, that is continuously in circulation. Why? Yesterday, if you recall yesterday's class, we had talked about the fact that different areas, they receive different amount of solar insolation across the planet. So in the lower latitude, you have the areas which are heat surplus, whereas in the higher latitude, you have areas which are heat deficit. So a method to distribute, or basically in order to distribute or transfer heat from the regions of surplus to deficit, etc., and to have a energy balance, that is why the air and the winds, they keep on circulating across the planet. Okay, so they basically circulate. So here, circulation of air does happen to distribute the heat, right, from the regions of surplus to the regions of heat deficit. Okay, so here, basically, when we talk about this air circulation or this kind of a wind movement, it is something which has been observed for a very long period of time. It is something which has been observed and basically tried to understand for a long period, because the sailors, the navigators, the mariners of olden days, they would basically rely on these winds to move from one place to another. That would be their source of energy. Earlier, you did not have these diesel engines, etc., which were steam engines, which would allow the ships to move from one region to another. You would be dependent on the sails and the winds, right? So they would basically come back and chart out the wind movement, and that is how people would become aware that why and how does this wind movement take place. Okay, there are certain questions that I tend to overlook. Okay, a couple of questions I will address and then we'll move ahead. Sorry for the interruption. So, sir, you gave an example from pole to equator, wind faces leftwards. How? Isn't it rotating towards the right too? Priya, is that issue of Coriolis force understood, or is there any doubt in that still after this? And you have another question. Doesn't it, in this case, the charged particles in cloud and heavier of the cloud results to rain in onshore winds phenomena? Or it also have patience. Have patience. We'll come to it. Take it up slowly and steadily, one by one, consume it. At the end of the day, if you retain the same questions, then let me know. Till now, take a look at these particular portions, try to digest it, and we'll come to the fact. See, even the cloud formation that you talk about, cloud formation is what? Can cloud formation happen without water vapor? Can ever there be a cloud formation happening without water vapor? No. So, what is the requirement for the cloud formation? The region needs to be abundantly having a lot of water vapor, which eventually will condense, will form the cloud. How will they condense? Eventually, they will rise up, etc. There is an entire mechanism involved, right? So, if you have the water body or winds coming from the water body nearby oceans coming over to the land areas, basically, they will bring moisture. That moisture can facilitate the cloud formation. This is the reason why, if you talk about these areas, they receive almost negligible amount of rainfall. Central Asia, Gobi Desert, etc. Negligible amount of rainfall. Why? Because they are very, very far away from any source of moisture whatsoever. Right. Similarly, even in India, if you consider, as we will study later on, that as you move in India from south to north and from east to west, the amount of rainfall reduces. Why? You are moving away from the source of moisture. So the onshore winds, they bring that moisture along with them, which then will facilitate rainfall. It is not as if that the wind is coming and along with the wind there are a lot of rain droplets and you have no cloud formation and you have rain droplets because of the wind. No, they bring moisture that will lead to cloud formation eventually, that will bring rainfall. Is that understood? Or is there a doubt in that? Coriolis force basically, Pavitra, is when we talk about the Coriolis force, it is basically the due to the rotation of planet Earth. Planet Earth, being a spherical object, does not rotate at the same speed in different places. So the speed of rotation can be zero at poles, can be around 1600 kilometer per hour at the region of equator. So when any object or any freely moving particle moves between these places of different speeds of rotation, it will experience a deflection. If it is moving in the northern hemisphere, it will experience a deflection to the right. If it is moving in the southern hemisphere, it will experience a deflection to the left. Any reason behind horse latitude regarding ship moves to the pole side? Okay. Gaurav, we have not even talked about the cloud formation. Please understand that. Okay. Please don't get any FOMO factor that this he has explained this in a jiffy and I am going to be left behind. No, just because that question mentioned about the cloud formation, that I will talk about cloud formation, thunder, lightning, everything, condensation, dew formation, everything I will talk in very great detail immediately after this module. Don't worry about it. Okay. Mansion and Rabi is decided based upon onshore and offshore. No, no. Okay, you are talking about monsoon. Monsoon is also a kind of an onshore wind movement. But the phenomena of monsoon is much more complicated than what you can imagine as of now. So, all this groundwork that we are doing, why is it that UPSC wants you to study this? Have you ever thought about it? I'm sure you would have been asking yourself and hitting yourself with that question almost on a daily basis. I wanted to be an IS officer. I wanted to be a district magistrate so that I can bring changes in the lives of people. And here I am studying about onshore wind, offshore wind, pressure gradient. How will it help me to understand what is happening in the district level? So UPSC wants you to study all this so that you are able to understand monsoons. Okay, that is how complicated a phenomena monsoon is. So the better you understand all of this, monsoon will be very simple, right? So that monsoon, I'm sure we won't be able to cover it by today. We will cover it next weekend. And after that, once you have understood the portion of monsoon, then you will always have the ability to take a look at the larger picture. You'll be able to relate economy with geography, geographical factors leading to economic crisis in many areas, how it can impact the political scenario in certain areas as well, the price rise that you observe due to unseasonal rainfall that happens. Why does that happen? Why is it that winter rains happen? Everything we will study immediately after the portion of all these climate, and that is where we'll concentrate upon Indian climate before looking at the world climate. So, okay, right now, see, the thing is, waiting for that. See, the thing is that just like I'm sure you would have played in your childhood days with a kind of a jigsaw puzzle, when you start putting the pieces of the puzzle together, it might have 1,000 pieces, 500 pieces, 2,000 pieces in that puzzle, but you will never get to see the entire picture unless and until you have put all the puzzles in place. So what we are doing as of now, think about it, is putting these individual puzzle pieces into its place. We are slowly and steadily building towards that larger picture. I'm sure by the end of the 24 modules, you will be able to, not even 24 modules, by the time that we are able to reach the 20th module itself, by that time itself, you will be able to see the larger picture in front of you. That if you are revising, obviously, how is it that geomorphology impacts climatology? How is it oceanography impacts the region around us? And how is it that overall it impacts the life in various places? That is the beauty of the subject. It comes slowly, but once it comes to your mind, then you will never forget it, provided you are gaining it from the conceptual point of view. Is cyclones arises due to, again, cyclones arises due to high pressure gradient? Yes, my dear friend. It arises due to a very high pressure gradient. Okay. So we were talking about why this air circulation happens. So the air circulation happens in a way, in a manner, basically to distribute heat from one region to another, right? Along with the oceanic circulations, etc. This is a very important medium to distribute heat. For a long period of time, the geographers, the climatologists, they always wondered that why is it that the wind will move across the planet, if at all? And will it move across the planet ever? So you had one of the first models which was postulated about the air circulation. And this was a model which was postulated by Hadley. And Hadley postulated what is referred to as the unicellular model of circulation. Hadley put forward what is the unicellular model of circulation. Now, what was this? Hadley's idea was based upon the thermal pressure gradient or creation of pressure zones due to temperature conditions. In the sense that he had an understanding that, look, the region around equator in the tropics, that will get heated up quite sufficiently. That will get heated up. So that means it will experience higher temperature. Now, when in the region, if you experience a higher temperature on the ground surface, as per Hadley, if this is equator, this is the region of the poles. He thought, and rightly so, that the poles are very cold, very, very cold. And the equatorial region is very hot due to heating. So at the region of equator, due to heating, you will have a low pressure because the air will rise up. The air will be rising up, isn't it? At least that is what Hadley basically had postulated. And air will rise up till what point? Till the tropopause. That is what we have seen in the circulation also. Air rises up till the region of the tropopause. After that, the air will diverge. It will be moving towards the poles. In the region of the poles, the temperature is very, very low. It is very cold. So here you will have sinking air. Now, if there is a sinking air, that means there's a deficiency or a vacancy created in the upper region. It will attract more winds. It will attract more winds. It will attract more winds. Here also, sinking air. It will attract more winds here. Now, that sinking air around the region of the poles will create a thermal high pressure. At equator, it is a thermal low pressure. At poles, it is a thermal high pressure. Winds will blow from a high to a low. Winds will move from a high pressure to a low pressure. So, from poles to equator. So, this was the circulation and the model of circulation which Hadley had propounded. Now, this circulation model completely was dependent on the temperature aspect of pressure, or the influence of temperature on pressure. Okay, so dependent on thermal influence on pressure. Only the thermal influence on pressure, that is what it was dependent on. Now here, when you observe this kind of a movement, when you observe this kind of a circulation, you have one circulation or one cell created in the northern hemisphere, one cell created in the southern hemisphere. That is why this was regarded as the unicellular model of circulation, because you have one cell in the northern hemisphere, one cell in the southern hemisphere. So that hence the name unicellular model of circulation. But then this was a kind of a circulation and this wind movement. As per Hadley, the wind on the ground surface would originate at the region of the poles and would move all the way to the region of equator. Now, can that happen? In the situation where you have Coriolis force, etc., you can never have the wind which is originating from here and reach here. At max, the winds, they will deviate, right, in the rightward direction. They will never be able to reach the poles. Similarly, in the upper atmosphere also, here also, in the upper atmosphere, in the region of the tropopause also, the wind cannot simply go from the region of equator to the region of the poles without experiencing so much deviation. So in the upper atmosphere also, the winds would deviate so substantially, it would never be able to reach the polar area. So that did not fit the bill. And also it was observed that on the ground surface, it is not always that the direction of the wind movement in the northern hemisphere is north to south and in the southern hemisphere it is south to north. No, you had different directions of wind movement which were observed. So from this, you had this particular model of circulation which was then modified. Total of 4 parcels. Where do we have 4 parcels, Subhash? Please let me know. Please let me know. How is it that we are talking about the 4 parcels? We are talking about one parcel or one cell in each hemisphere. Hence the name unicellular. Okay. Is that understood? Or what 4 parcel are we talking about? Hadley concept confused. Okay. See, Hadley postulated what was referred to as the unicellular model of atmospheric circulation. As per this model of atmospheric circulation, around the region of equator, the ground gets supremely heated and gets heated quite significantly. When the ground gets heated here, that means you will have a thermal low pressure, right? Because temperature upon heating, it will create the air becoming warmer, will tend to become lighter and it will rise up, right? So low pressure at the region of equator. And also at the region of the poles, because of very cold conditions at the region of the poles, because poles the temperature is very, very low. So at the region of the poles, you have the presence of high pressure. Okay. So here, that is where Hadley said that there is a circulation between the high pressure at the poles and the low pressure at the equator. So from equator, the air will rise up. After getting heated, it will hit the top of the troposphere. Then it will diverge It will go towards both the region of the poles. It will then sink and cool down, and then it will again get moved towards the region of equator. That was the circulation. That was the kind of unicellular model of circulation postulated by Hadley, which talked about the presence of only one cell of circulation in each hemispheres. Okay. Subhash, north, right, and left, two cells, and south, right, and left, two cells. No, my dear friend, Subhash, understand. See, this is a 2D image. That is why you are finding that kind of an issue. It is basically only one cell, only a complete area around the Earth. You will experience, as per Hadley, in the northern hemisphere, a circulation, in the southern hemisphere, another circulation. Okay. Now, this was later on, it was understood to be flawed, significantly flawed, and you had the development of another model of circulation, which we follow till today. That is the tricellular model of atmospheric circulation. And tricellular model of circulation, basically, here it kept into account the bending due to Coriolis force of action as well. So that is something that we will take a look into, and we'll take a look into it after the lunch break. So let's take the lunch break now, and we come back at 2, and then we continue after the lunch break. Okay, we continue with the tricellular model of circulation, the pressure belts, and then we talk about the what happens actually and the local winds. Okay, so let's take a break, and we'll be back at 2 p.m. Okay.